Let me see if you remember what alternating series test does. It requires two conditions, right? What are the two conditions? Alternating series is when you have something that's plus and minus alternating.
Did it have a bigger thing? Oh, never mind.
So,
Okay. Yes.
would McLaren technically be alternating them?
Maclaurin series of the sine or cosine, those are alternating series. Okay. So when do we know that an alternating series converges? If it meets two conditions.
A of n plus 1, the absolute value of A of n plus 1.
Right. If these terms are decreasing.
Right.
Yeah. Second.
Second, A n has to be positive, and the limit has to be 0.
Okay. So if these two conditions are met, usually I write this first and then the next. If these two conditions are met, you should have the following mental picture in your mind. It's really important that you don't just think about this as equations, but as a mental picture of when it's plus, it's going right. When it's negative, it's going left, right? And the first thing says, this one says, as you go back and forth, the jumps are getting smaller and smaller. The second one says, eventually it gets smaller and smaller to 0. That's the idea, okay? And of course, if that happens, right, if it's going back and forth and it's losing energy and it's getting closer and closer to 0, it's going to converge to some place. That's what the alternating series test tests for. If those two conditions are met, we know that it converges, okay? Now, it doesn't mean that if any of these are violated, it will always diverge. That's not what it says. However, we do know that if any of these are violated, you do have some examples where this will diverge. And the questions I wrote down here are asking exactly that. So for this first question, we're accepting that the limit an does go to 0, but let's say we remove this condition that the jump sizes are getting smaller. Okay? Then can you think of an example where the sum will diverge? Well, that's a very hard question if you haven't seen the example. And since I've never shown you an example, I don't think you can come up with the answer. But despite that, I still want you to think about the following. If the jump sizes are not getting smaller, but they're still going to 0, what can happen? Well, you might be able to come up with an example where you're always moving right with a bigger jump than when you move left. So you might be going right as a bigger jump, but you're only going left slightly. Go big jump slightly, big jump slightly, big jump slightly. So eventually what happens is that the movement towards the right is always bigger than the left one, so you end up getting infinity as your sum. Does that make sense? That could happen, right? Okay. So that's the idea. Huh?
What does that look like?
So I'm going to write you the answer for this one.
But I can't think of anything that would look like that.
You'll see. So the one, well, of course, there are many possibilities, but one thing I want to show you is this case. Let A2m equals to 1 over m, and A2m minus 1 equals to 1 over m squared. It's a little confusing even seeing this 2m. When I write 2m where m is an integer, what does that represent? 2m means it's an even number, right? So any even term of this series, I want it to look like 1 over m. That's what I want, okay? On the other hand, what is this? 2m minus 1.
Real.
It will be an odd, because if you have any even number, and you subtract 1 from an even number, that's any odd number, right? Any odd number is 1 less than an even number. And that's what this is saying, right? And for those, I want 1 over m squared. Now, you already see what's going on here, right? Sum of 1 over m squared is some... Does this converge or diverge?
It converges.
It converges, right? On the other hand, if you add up 1 over m, it diverges. That's a harmonic series, right? If you add up all the... So that's exactly the idea that I have. One side goes to infinity, this one gives you some finite value. All right? So now, yes?
Since we want a negative jump, but then a bigger positive jump, wouldn't we want that one to be alternating?
Well, look, I have negative 1 to the nth power, right? So here's what we have. Then, summation of n from 1 through infinity of negative 1 through nth power of any n is same as summation from m equals to 1 through infinity. So if you write this, the very first number is when n is 1, right? That's same as negative 1 to the 2m minus 1 times 1 over m squared. Okay. This is your 1 and 1, right? Because a1 is what? a1 is 1 over n, 1. That's exactly what you have when n is 1. But then when n is 2, that corresponds to when m is 1 with this one, right? So that's going to give you plus negative 1 to the 2m, 1 over m. So what I just did was I just rewrote this as separate formulas for even case and odd case and even case. Yes?
But why is a2m and then a2m minus 1m squared?
No, I'm just choosing this. I'm just giving you an example. It says find an example, right? So this has like many possible answers. Out of all that, I'm just demonstrating that if you choose a2m to be 1 over m, and if you choose a2m minus 1 to be 1 over m squared, then this example exhibits the behavior I talked about. Like going right, you jump more than going left. See, this is a lot bigger than this one. When m is 10, what is 1 over 10 squared? That's 1 over 100. Right? And this is 1 over 10. 1 over 10 is 10 times bigger of a jump than going left, which is 1 over 10 squared. Well, yeah. So when m is 10, that's like a20 will be a jump of 0.1 to the right. But then a19, the one step before that, would have been 1 over 100, which is a lot smaller jump to the left. Now, you can see why I'm saying that this is a left jump and this is a right jump. Look at this. What's negative 1 to the even power?
It's going to be an even
Positive.
If you take negative 1 to the even number, you get
A positive number.
positive 1. Yeah, positive 1. If you take even power, it's positive 1. How about this one? Negative 1 to the odd power is?
Negative.
Negative 1. So this is really saying you have summation of negative 1 over m squared plus 1 over m. M from 1 through infinity.
We put 1 over m because you want it to equal to 0, right?
We put
1 over m. Yeah, right.
So because we have this condition, that's why I have the examples as 1 over m and 1 over m squared, because they both satisfy this condition.
Yeah.
Yeah. So you can see that this satisfies all the conditions that's needed. Right? So already here you see that this has to be positive, because if you add 1 over m, what do you get?
You get a positive number.
No. If you add up all the 1 over m's,
Oh, you get infinity.
infinity, right? But if you add up all the 1 over m squared, you get
Negative.
some
Some
negative
number.
positive, a negative finite value.
Right.
Because 1 over m squared
Converges.
converges, right?
Mhm.
Actually, I know the value. It converges to negative pi squared over 6. Okay? So this part converges to negative pi squared over 6. But even if you didn't know that, you know that it's some small value. Right? On the other hand, this gives you infinity, and infinity minus pi squared over 6 is still infinity. Right? So that's why this is infinity. Now, what I just said is slightly wrong because I'm assuming that you can just add this one separately and this one separately and then add them together, which is, by the way, not permitted. If you have some series that's not absolutely convergent, this is divergent, so it's not absolutely convergent. In that case, you can't just switch order of addition. So that's dangerous. So even if what I'm saying here may have made sense to you, the correct way to prove here to there is you have to rewrite this as m over m squared. So this is like m minus 1 over m squared. If you put these two fractions into one, this is what you get, and then you do the limit comparison test with 1 over m, because this limit goes to 1. And because this diverges, the sum of that 1 over m diverges, some of this has to diverge as well. That's the proper way to do it, but you know, if this was an exam problem, if you wrote this, I'll be happy to give you full credit. Okay. All right. So you get my point, right? Is that good? All right. Now let's look at the second example. Find an example of a series such that you have positive. Oh, again, it's an alternating series. And this time you do have decaying jumps, right? The jumps are becoming smaller and smaller. But what's not assumed here? What's missing? What condition is missing?
The limit is not.
So here, notice that limit n going to infinity of an equal to 0 is missing. Okay. This condition is missing. And therefore, because it's missing, there are cases where even if this is true, it might be divergent. The summation might be divergence. Okay. So what? Answer. So think about this. Your jumps are getting smaller and smaller, but it doesn't go to 0. What could happen? What would happen if it goes to, say, 1? You're going back and forth. It is getting smaller.
Oh, it just goes back and forth between two numbers.
Between two numbers and never converges, right?
Mm-hmm.
Yeah. So actually, that's what we want. We want something that gets close to 1. So I want something whose limit is 1. It's decreasing, but its limit is 1, so that you end up just going back and forth. Such a series wouldn't converge, right? So give me an example of a function that would get closer and closer to 1. It's decreasing, but getting closer and closer to 1. Can you give me an example? Huh? No.
E to the y.
Either, is that
Give me a function of x that goes down like that.
Oh, that's
One over root of x.
Yeah, those all go to 0. ln of x goes like that. It's not.
Negative ln of x?
No.
Goes to 1, you said?
ln of x doesn't have any horizontal asymptotes, so that's wrong. I want 1 as the horizontal asymptote.
X plus 1?
Yeah, 1 over x plus 1. Right? That would have horizontal asymptote as 1, right? Yeah. Okay, so that's what we want to use. I want to say an is 1 over n plus 1. Then an plus 1 would be replacing this n by n plus 1. And this is indeed less than 1 over n plus 1, because here you have bigger denominator than this one. So overall, this fraction will be smaller than this fraction. And this is an. So we do satisfy this condition. On the other hand, however, summation of n from 1 to infinity of negative 1 to the nth power of 1 over n plus 1 diverges. Why? Well, we know the answer intuitively, right? Eventually, when n is really big, this value, this jump becomes 1. So you're just going back and forth by 1, right? But we wrote all the tests down. Of all those tests, which one can be used to show that this diverges?
Easier.
It's not P series.
The absolute convergence.
Nope, it's not.
Integral test.
By the way, absolute convergence test can only be used to show convergence. Same with AST. Okay? There's some tests where you can only be used for one thing. So, for example, the test for divergence is only for divergence. AST and absolute convergence is only for convergence. Huh?
The
Nth term test, that's the one. Yeah. The test for divergence. Okay. So because of the nth term test, because if you take limit n going to infinity of negative 1 to the nth power 1 over n plus 1, this doesn't converge because every even term goes to positive 1 as your limit, but the odd terms go to negative 1 as your limit, so your limits are different for even terms and odd terms. So this limit does not exist since the even term limits and odd term limits are different. The limit does not exist. Because of the nth term test. Or you can also say test for divergence. They're the same thing, right? Some people call it the nth term test, some people call it the test for divergence. So that shows that indeed, if you remove this condition, there are examples where the series wouldn't converge. Okay. So these two are good examples to think about why the alternating series test has those two conditions. One is that the limit has to go to 0, and second is that the individual terms has to be decreasing.